like integrating that to like the left hand side, and then just like figuring everything out.
Okay.
So like, is there any tips like you could give? Or anything?
I mean, it is a lot of algebra. I would say, if it helps, I would say just plug in the numbers earlier into the problem. Basically, as soon as you have the velocities, plug those in. I think the thing that's difficult about the problem 2 on the homework is that I gave you it's a variable velocity problem. So the velocity is not constant.
That's what's right now.
Yeah,
I still don't get it. I sat there for like 2 hours staring at my screen, like I don't know what to do. I can't figure it out.
Yeah, just take it one step at a time. And so I would plug in everything except for the x values. And then when you plug in for, you're applying that equation at the different nodes, like node 2, node 3, node 4,
Sure.
Then you plug in for x there. So plug in everything up until that point, and then save the x stuff for at the very end.
Okay.
So when we don't apply the xi.
You do eventually, but I would say that to the end, because that's kind of the most complicated.
So like once you're actually evaluating it at each node, then that's when you would plug it in.
Exactly,
Okay.
because each node has a different x.
Right. And then the xi is found with the I minus 1 times delta.
Exactly.
And then j minus 1 times delta for the yi.
Exactly.
Okay.
Exactly. Yeah.
So then that you have to find my answers wrong.
Okay.
40 magically turned into a 4.
Okay. All right.
That's step 2, and I was wondering why nothing makes sense.
I see. It's a lot. And I think conceptually there's a lot going on, but there's also a lot of just algebra and a lot of stuff going on too. So yeah, definitely take your time with these problems. They can be challenging.
I think I just heard the answer to the mistake I was making. It's very painful.
Oh, really?
That's a very painful answer to hear. I just couldn't. All it's been is I don't know how to. I was like, how do I replace this xi with something meaningful that actually does anything?
Oh, yeah. There you go.
I didn't know what the xi or yi meant either until I went digging through the notes and I saw that it was somewhere in the notes.
Yeah,
And then I just assumed it was that and everything kind of worked.
I read through everything and I just missed it, I guess. Yeah, I was like week 5, I think, around there. Oh, I hate that. The last thing I was reading was week 6. So I must have just skimmed through week 5 too quickly. Okay, all good. It's all good because now it makes sense.
There you go.
I had Jerry was explaining to me all it's showed out like an hour and a half history stuff.
Yeah, it was very funny. I had Jerry and Diamond both being like, "This is how you do it." I'm like, I don't get it.
No, exactly right. They're like, just read the notes. I'm like, I am reading. Them.
What do you think I've been doing for hours?
Wait, Professor, for the 1D, does it matter if you start with phi I plus 1 or phi I minus 1?
No, it doesn't.
Doesn't? Okay.
Yeah, I'm just.
Because it was written both ways in my notes and I thought I was.
No, because it's an algebra equation, so you can swap the term. If anything, the phi I minus 1 first might make more sense because then it drops directly into the matrix a bit easier, but it doesn't matter which one you have first.
But then once you have everything, you plugged everything in, is it just matching the coefficients for the
Exactly.
values?
Exactly. Yep.
I think Jerry is somebody. I mean, just a play.
All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today?
Great. Hope I'll be back.
I know. It's the class before the midterm, so this is always not a fun. Well, it's a stressful class, so I understand. We're not going to cover anything that's on the midterm today, so we're starting something new. This stuff is going to be on, it's going to be important later in the class, of course, but you don't need to know this before Wednesday. Okay. We're doing unsteady problems, and so I think this is the part of the class where I think people kind of start getting excited about it because the results are fun. Okay? Because what you'll see is that when you have an unsteady problem, you have things that change with time. And so when we run our codes now, usually when we run our codes, our result is just a static figure. But after today, when we run our codes, you're actually going to get a video or like an animation of something changing. And so I think this is where I think the class really gets fun, because these problems are normally very, very difficult to do by hand. Okay, so announcements. Remember, the midterm exam is this Wednesday, and so make sure you guys are here for that. So, for those of you on Zoom, remember there's no, you won't be able to take the exam online or virtually, and so please make plans to be here in person on Wednesday. Okay. Just a reminder of what you can bring. Remember, you can bring your writing utensil, you can bring a calculator, and you can bring a cheat sheet. And so your cheat sheet is a single 8.5 by 11 sheet of notes. You can write both sides. You can write it, you can type it, whatever you want. Okay. I usually like to collect those just to kind of look at them. And so, if you want to keep it for later in the class, please write your name on it. Okay. Let's see what else. Homework 3 members due tonight. I know a lot of people have been working on it. So I know homework 3 is due kind of right up until, I know we're kind of pushing it close to the midterm. But again, remember, I designed homework 3 to really give you kind of good practice for the exam. So if you can really nail down problem 2 on the homework today, then I'd say you're in really good shape for the exam. Okay. And so I'll be posting solutions for homework 3 pretty much right before I go to bed tonight. So right around midnight. And so you can definitely have those available to you to study tonight. Okay. Okay. Other announcements? A question? Yes.
Will the problems on the exam be as long as the ones on the?
No. There'll be a lot shorter than the ones on the homework, for sure. Yeah, I know. It's a lot of writing. It's a lot of algebra. And exactly. So for the exam, you're only going to have 75 minutes to do the exam, and so they will definitely be, time will not be an issue on the exam. So the problems will be shorter, and usually for this I give 3 problems, but I think 3 kind of workout problems. But I think this time I'll probably give 2, just so you can really kind of focus on that and not have to worry about the time. Okay. Okay. All right. I think that's all my announcements. Are there any questions about the exam or anything that I can answer before we get started for today?
So it looks like to me like 2 workout problems, and like the rest is like what you do typically conceptual.
Exactly. Yeah. So two workout problems. So I'll probably give you 2 differential equations. Probably going to be one 1D problem and one 2D problem. That's what I'm thinking of right now. And then there'll be 4 or 5 short answer questions.
We get like
Yes. Yeah. One 8.5 by 11 sheet. You can write anything you want on both sides. Yeah. Any other questions on the exam or anything? You guys may not be that happy, but I will say I'm very happy to see you guys today, because I had a almost near-death experience over the weekend. I went. One of my really good buddies is getting married in a month, so we had a bachelor party in Mammoth over the weekend. He really likes snowboarding. The problem is snowboarding in a blizzard is not a fun experience, and there were most of the time I couldn't see more than 10 feet in front of me just because the snow was like blowing. It was complete whiteout, so we couldn't read the signs going down. We kept getting lost. We kept getting buried in the snow. So it was there were some times, there's no point where like I felt like we were going to die right there, but there are definitely times where like, man, we're in trouble. So somehow I made it back down, and I told all my loved ones that I love them as soon as I got down, and thank God is good. As soon as I got down, so I'm very happy to see you guys today, even though I'm exhausted. Okay, so let's get started with the lecture for today. Okay, so we're starting something new. A question, will there be a question about the exam? Will there be a question to continue MATLAB function or fill in the blanks of code? There will be no coding on the exam at all. So it's all just conceptual stuff. Yeah. And actually, if you check out you probably got the announcement about an hour before class. If you check out the review video that I posted, that is a great example of kind of what I expect of you guys on the exam. So on the review video, I did one 1D problem, one 2D problem. If you can get that, if you can get problem 2 on homework 3, I'd say that's gold. So you guys are gonna be good for the exam. Yeah. So there's no coding at all. Okay. Okay. All right. So today, we're, like I said, we're starting something new, and we're going to be doing unsteady problems for the first time. Okay. So far, what I would say is we've covered the two main physical mechanisms that have to do with heat transfer. So we've gone over diffusion, which is basically heat conduction, and we've gone over convection. Okay. So kind of the last, I would say, dimension that there is to these kinds of problems is the fact that these heat transfer situations or transport situations can change with time. Okay. Right, because if you notice, everything that we've done up to this point has been steady state, right? And so we have a diffusion equation, maybe a diffusion convection equation, and we solve it. And our result is just a single, basically like a snapshot, right? And so we get a snapshot of what the temperature field will look like, or what the phi field would look like at a single instant of time. Okay. So that's good. There's a lot of situations that fall under that, but I would say a lot of the really interesting situations in engineering practice are ones that actually change with time. Okay. And the interesting thing is that, you might think that it's, it may not be that big a deal because we've already learned a lot of, computational tools. But the thing is time behaves very differently than in space. Okay. And so because of that, we're going to need kind of almost like a whole new set of tools to deal with, these kinds of situations. Okay. All right. And so what does it look like? So just like we did with convection, let's start with the 1D case. And so our 1D equation looks like the following. So we have partial phi, partial t, okay, plus u, partial phi, partial x, is equal to k, partial squared phi, partial x squared, plus q of x. Okay. All right. So our differential equation, or the equation that we're solving, is it grows with every lecture. Okay. And so let's go ahead and label these terms. And so first we have partial phi, partial t. So this is our unsteady term. Okay. We know that's the unsteady term because it's the only derivative with respect to time. Then we have our convection term. So that's what we just kind of finished talking about. So remember, the convection term is characterized by a first order derivative in space. Okay, so we have partial phi, partial x, and then a velocity, which is u. We have our diffusion term. Our diffusion term is still the same as always. And so we have a derivative, second order derivative with respect to x. And our last term here is our source term, which is basically any other additional function that does not have phi. Okay. All right. So like I mentioned, it may look like we're just adding another derivative to this, right? And so, we've done, you know, we've taken on two derivative terms at this point, right? We've taken on the diffusion and the convection derivative. And so adding on another derivative, you know, may seem like, you know, it's not that big a deal. We'll just do the same thing as we did before. Okay. But time, you know, if you notice here, time is now an independent variable. It's not just X. Okay. And so the way that we deal with that is different. Okay. All right. And so, you know, the methods that we'll go over in this class, I would say that, you know, in normally, and I would say normally this is also a graduate level class. Normally, you know, you would dedicate almost an entire class to the types of algorithms that we're going to be covering here. Okay. Obviously, we don't have a whole semester. We have maybe about 3 weeks to cover time marching. And so we're just going to be going over the basics of the basics. But, you know, I want to kind of introduce you to the fact that this kind of belongs to a broader class of algorithms. And so the name of the algorithms that we'll be doing are called time marching schemes. Okay. So, you know, that name there is actually pretty good because, you know, the way these algorithms work is that we literally march the solution forward kind of one time step at a time. Okay. And so we're going to solve for the solution at one time step, and we're going to use that solution and march it forward one step, solve for the next one, and so on and so forth. Okay. There is a lot of research out there in terms of time marching schemes, and there's more different types of time marching schemes than there are, you know, probably students at, you know, in this whole building at this time. So it's a very intense area of research. And so, you know, we'll be going over, I'd say, the essentials, but, you know, it goes, just to let you know, it goes kind of a lot deeper for this. Okay. Yeah, quick question, sure. I'm assuming you're typing the question, Victor. For homework problem 2B for the 80, did I use backward difference? If the 80 is a positive velocity, then yes, I use backward difference. But if the 80 is a negative velocity, then I use forward. I think I used forward difference on it because it was negative. But yeah, I'd have to double check. I don't remember the sign off the top of my head. Yeah. Mm-hmm. Okay. All right. And so just like I mentioned, you know, the results that we're going to get from this are different. And so because our solution here is going to be evolving with time, that means our solution is now going to be, is also going to evolve with time. So that means it's going to be an animation. We're literally going to be solving, you know, the solution one frame at a time. And basically the same way that you understand videos in terms of, you know, videos are just kind of a bunch of still images just stitched together very quickly. That's basically what our solution is going to be as well. Okay. All right. So that's kind of where we're going for today. And so, you know, my plan for today is to kind of introduce kind of the simplest form of the of time marching, which is called explicit Euler. And then we'll do an example at the end today. Okay. So no, there's no code for today. All right, any questions on anything today so far? Okay. All right. All right, so let's talk some notation. So because, you know, we're adding kind of an extra dimension here, we have to kind of change our notation or use a new notation to denote time. Okay. And so before, before today, we've used our IJ notation. We use IJ notation to denote kind of where a node, a particular node, is located physically in space. And so, of course, that's in 2D. In 1D, we just had the I notation, right? But basically, we had this IJ to denote kind of where it is, right? So when we usually write our phi, right? The IJ was in the subscript, and that told us kind of where that node was physically. Okay. All right. And so we're going to use another script here to denote time. Okay. And so for time, we're actually going to use superscript. It's going to go in the exponent location right there. So this right here is what I call the time index. Okay. And the time index lets you know kind of when this solution is has taken place within the time scale. Okay. Okay. All right, so for example, I'm just going to do a 1D case here. Okay. And so in 1D, we always solve our solutions on a numbering line just like this. Okay. And we have all of the subsequent values. Okay, so phi1, phi2, phi3, phi4, phi5, phi6, right? So that subscript there tells you where, physically where or spatially, I should say, where the solution is taking place, whether it's on the left side towards phi1 or towards the right side, phi6, and then everything in between. Okay. And so for an unsteady problem, what you're going to have is that for the same domain, okay, so for the same domain, and so we have the same 6 nodes here. We have the same solution values, so phi1, phi2, phi3, phi4, phi5, phi6, okay? And so let's say between the top figure and the bottom figure, some time has passed. Okay. And because we're in an unsteady problem, the values for phi at the same physical locations are going to change, okay? And so one way we can denote this is we can say that this is on the top here. We can use a time index of 1. So I'm going to put a 1 on all of these. And then after some time has passed, we can say their values are now going to be 2. So let's just focus on just one of these nodes. Okay, so let's look at phi2. Okay. And so just imagine for a second you're standing at the location of node 2. Right? So you're standing there, right? You're not moving, but time is passing, right? And so as you kind of stand there, you can notice that the value of phi is going to evolve, right? Because it's an unsteady problem. And so that's basically what it means to change with time. And the way that we denote that is through that superscript. Okay. And so now we're introducing, it's a lot of subscripts to remember, I know, but just know that when we're in the superscript, we're making changes in time. Subscript is denoting kind of spatial location. Okay. All right. Any questions on the notation? Okay. All right. And so with that said, let's introduce the concept of an initial condition. And so very similar to how so far, when we solve our problems, we needed boundary conditions to kind of, you can kind of think of it as close the loop and sort of complete the solution. Okay. When you're talking about time evolution, kind of the equivalent to that is an initial condition. Okay. And so what an initial condition does, it defines how the solution is spatially distributed, is how the solution is all points in space at the initial time t is equal to 0. Okay. Or in other words, n is equal to 1. Okay. And so we need this to solve for, to solve our equations. So this will make a bit more sense once we actually start doing a problem. But the initial condition, usually, we spend a lot of time talking about boundary conditions, and for good reason. Boundary conditions are pretty complicated. For initial conditions, they're not as bad. So usually what we assume for initial conditions, just for the sake of convenience, is we assume what's called a blank initial condition or zero initial condition. Okay? And so what that basically means is that we make the assumption that when our simulation starts, all the values of phi, or all the values of our solution, start with a value of 0. Okay. So 90% of the time, that's what we're going to assume. And it makes coding it pretty simple as well. Okay. All right. So let's go back a little bit to this notation here for phi. Okay. And let's talk about how we actually use that in a time marching algorithm. Okay. Okay. And so in a time marching scheme, it doesn't matter which time marching scheme that you're looking at. Okay. The goal is always the same. And so the goal is to solve for the solution at the next time step, given that you know the solution at the current time step. Okay. All right, and so how do we denote this? And so we usually use two different types of n's to denote this. Okay? And so n plus 1, okay, that's the notation that we're going to use for the next time step. Again, this is unknown for now. Okay. And then time step n, this is the current time step. And this is known. Okay. So we're always trying to solve for the solution at n plus 1, given that we know the solution at time step n. Okay. And so in other words, mathematically it looks like this. So phi I comma j at n plus 1. Okay. That's what we want to know. And then, but what we do know is the solution at time step n. Okay. So we have phi I comma j at time step n. Okay. And then what I'm going to do is I'm going to put an f outside here to denote the algorithm. Okay. Okay. So basically what this is saying is that the solution at the next time step n plus 1 is a function of the solution at the current time step n. Okay. And so again, I know all this is just kind of very foreign at this time, but it's kind of a necessary evil. And so in order to start talking about the algorithms, you need to know the notation, but it's hard to kind of understand the notation without the algorithms. And so you kind of have to start somewhere. And so I usually like to start with the notation, and then once we discuss the algorithm, then things make more clear. Okay. All right. Any questions on this so far? All right, and so with that said, let's jump into our first algorithm, which is called explicit Euler, or Euler, or however you want to pronounce it. Okay. For Dude being so famous and for developing so much in applied mathematics, no one really seems to know how to pronounce his name. And so, half the people say Euler, half say Euler, no one can ever agree. Okay, so let's see how this works. And so the key word here is actually not his name, it's actually the word explicit. Okay. And so explicit Euler or explicit Euler is not the only explicit time marching scheme out there. Okay. But I will say probably one of the more popular types of time marchings just because of its many properties. Okay. And so explicit time marching schemes, we're going to be looking for the solution at the next time step. And the way that we're going to do this is through just regular matrix multiplication. Okay. It's a matrix vector multiplication. Okay. So this is actually quite different than what we've done, right? Because everything we've done up to this point, when we solve for the solution, we've had to use we basically had to solve a linear system of equations, right? And so in MATLAB, that involved using the backslash operator. Okay? And when we're doing by hand, we just don't even try. We just say that, here's our linear system and we can solve it somehow. But the thing with explicit schemes is that these are actually a lot easier to solve by hand because you can actually perform the multiplication a lot more easily. Okay. And so that's kind of the appeal of explicit algorithms, that they're mathematically very cheap to do, but it also has a lot of downsides that we'll talk about soon. Okay. All right. So let's see how this is performed. So let's start with our general equation. So we have partial phi partial t plus u partial phi partial x is equal to k partial squared phi partial x squared plus q of x. Okay. So that's the equation that we started with at the top today. Okay. All right, I'm going to do one step here just to make things a little bit easier. And so all of the spatial terms, I'm going to move to the right-hand side of the equal sign. Okay. So I'm going to take this convection derivative and just move it over there. So we have partial phi partial t is equal to negative u partial phi partial x plus k partial squared phi partial x squared plus q of x. Okay. So first thing I'm going to do is, just like we usually do in these type of situations, let's replace all the spatial derivatives with a finite difference approximation. Okay. And just to keep things simple for now, I'm not going to worry about the direction of the velocity. I'm not going to worry about upwinding. And so I'm just going to use a central difference for the convection. Okay. All right, so the time derivative, I'm just going to leave alone for now. Okay, so it's going to be partial phi partial t is equal to minus u phi I plus 1 minus phi I minus 1 divided by 2 delta x, okay, plus k phi I plus 1 minus 2 phi I plus phi I minus 1 divided by delta x squared plus q of x. Okay. So far, nothing too drastic. And so, we've basically just done the same as we've always done. Right? Next step is going to be to actually discretize the time derivative term. Okay. And so we're going to use finite differences on this too. Okay. The difference here is that, because this is a derivative in time, not in space, we need to make sure we handle this derivative, using our brand new notation. Okay. And so the finite difference approximation of partial phi partial t is going to be phi n plus 1 at I minus phi at n at I divided by delta t. Okay. So you notice the differencing now is on the superscript and not on the subscript, right? So we're leaving I alone, and the superscript is going from n plus 1 to n. Okay. And then everything else on the right-hand side, we're going to keep the same. So minus u phi I plus 1 minus phi I minus 1 divided by 2 delta x plus k phi I plus 1 minus 2 phi I plus phi I minus 1 divided by delta x squared plus q of x. Okay. I'm going to pause here for a second because the next step I think takes a bit of explaining to do. So I want to make sure that everyone's kind of catches up to this. Okay. So our goal, if you remember kind of when we defined time marching schemes, our goal is to come up with an equation for phi I n plus 1, right? So this right here is our goal. And so essentially what I'm going to do is I'm going to manipulate this equation to solve for phi I n plus 1, okay? But before we do that, before we do any algebra, there's one thing we need to do, okay? And what I want to draw your attention to is everything on the right-hand side of this equal sign. There's something missing here, and that something missing is going to be key to our algorithms, okay? And if you'll notice what's missing, all the phi values here do not have a time index. They have a spatial index. They have the i's and I plus 1s and I minus 1s, but there's no reference in terms of when these solutions are actually taking place. Okay? So we need to assign these, and so we can't just leave it like that. Okay. And so we basically have two options here. So we can assign them either n plus 1, the next time step, or we can assign them at n, the current time step. Okay. So initially, what we're going to do for explicit Euler is we're going to assign all of them to the current time step. Okay. And so we're going to put an n in the superscript for all of those other phi terms. Okay. Because that's necessary, because we need that to solve our equation. Okay. All right, so now that we've assigned the time step values for all the other phi terms, we can go ahead and work on this algebraic. Okay. So let's isolate the phi I n plus 1 on the left-hand side by kind of moving things over to the right. Okay. All right, and so the first thing we're going to do is we're going to take the delta t. We're going to multiply that on both sides of the equation. So we're going to have delta t throughout. And then we're going to also add this phi I n to the right-hand side as well. Okay. All right. And so after that step, this is what it looks like. And so we're going to have phi I n plus 1 is equal to minus u. Let me do this too. Let me bring out the entire constants. We have minus u delta t divided by 2 delta x multiplied by phi plus 1 minus phi minus 1, both at time index n, okay, plus k delta t divided by delta x squared multiplied by phi plus 1 minus 2 phi plus phi minus 1, all at time step n. Okay. We have our extra phi n that came from the time derivative. Okay. Okay, so we have another one of those. And then we have q of x times delta t. Okay. So it's a little bit messy, and so I know there's a lot of symbols kind of floating around, but just try to kind of write everything down, and then we'll kind of check it afterwards. Okay. All right. And so from here, we're almost done here, which is a good thing. The last thing we're going to do here is we're going to group together the like terms of phi. So just like we did in convection. on the right side. Okay. And once we do that, we're going to arrive at our explicit Euler equation. Okay. All right. And so if we do that, we get Ti n plus 1 is equal to U delta T divided by 2 delta X plus K delta T over delta X squared. All this is multiplied by phi I minus 1 at n, okay, plus 1 minus 2k delta t divided by delta x squared, phi at n, plus minus u delta t divided by 2 delta x, plus k delta t divided by delta x squared, phi plus 1 at n, plus q of x delta t. And so this right here is our explicit Euler time marching equation in 1D. Okay. It looks like a mess. I know it looks like a mess. But what you'll see is that once you actually have some numbers in this, a lot of this actually simplifies quite a bit. Okay. There's just a lot more going on now because we have both diffusion and convection, and now we have the unsteadiness as well. Okay, so there's a lot of it. But hopefully, all the steps that we did here makes sense. And so, with the exception of, some of the new time marching stuff, everything else is kind of, the same. So we're kind of just building on kind of all the methods that we've picked up so far. All right, any questions on this? Okay. All right, so let's do an example just to see how this actually works and how do we actually use this. Okay, so this equation here is nice, right? It's nice to kind of show off to your non-engineering friends. Okay? But it's not, as it is right now, even I would admit it's not really that useful. And so let's see how to actually use this in an example. Okay, so let's do a very, very simple problem. So let's do an unsteady diffusion equation. Okay. And so for unsteady diffusion, we have partial phi, partial t is equal to 3 partial squared phi, partial x squared. Okay. And we have our boundary conditions. Okay. So we have phi at x is equal to 0, and all values of t is equal to 1. And our other boundary condition is d phi dx at x is equal to 1, and all values of t is equal to 2. And then we also have our initial condition, where, remember, this is the initial value of the solution. And so what the initial condition states is that, we're going to start with basically a 0 initial condition. So at all values of x, when t is equal to 0, our phi is going to equal to 0. Okay. And so what we're going to do with this equation is we're going to use explicit Euler with a time step size of 0.1, so our delta t is going to be 0.1, to solve for the solution on a 5-node grid. So our grid here is going to have 5 nodes, and the grid spacing physically in between 2 nodes, delta x, is going to be 0.25. Okay. All right, so that's the problem. So what we're going to do is we're going to use this equation up here, okay, to solve this equation forward in time. Okay. Any questions on the problem setup here? All right. So let's go ahead and plug into our explicit Euler equation. So we have a lot of the parameters here already. So we have delta t, we have delta x, okay? The only other things that we need are going to be the values for the diffusion constant k, as well as the convection velocity u, okay? Once we have those settled, we can just kind of plug in for everything. All right, so let's do k first. So k is the diffusion constant, and so it's just whatever coefficient is in front of the second order derivative. And so in this case, we have our second order derivative here in the equation. Okay? And we can see that the coefficient in front of that term is 3. Okay, so in this case, k is equal to 3. And so the other thing we need is the convection velocity. And so in this problem, there is no convection velocity because there's no first order derivative in space. And so u here is going to be equal to 0. Okay. And so let's plug all that in. Okay? And what you'll see is that after you plug all this in, it actually simplifies this equation quite a bit. Okay? Oh, one more thing. So the source term. Remember, the source term is defined as any other functional part of the problem that does not involve phi. In this case, our source term is also 0. Okay? So we don't have to worry about that. Okay. So let's plug all this in. And so what we get is b I n plus 1 is equal to 4.8 b I minus 1 at n minus 8.6 b I at n plus 4.8 b I plus 1 at n. This right here is our time marching equation. For this problem. And so from here, you can probably guess the next step, right? And so just like we did for all of our SETI problems, what we're going to do is we're going to use this equation, apply it for as many nodes as we can, and we want to get basically an algebraic equation for each node in our grid, okay? So let's say use this together with the boundary conditions. And then from that, we're going to obtain an algebraic equation for each node. Okay, so let's do this. And so just like we did before, now you make space for all 5. Okay. Okay, so we're going to have an equation for I is equal to 1, I is equal to 2, I is equal to 3, 4, and 5. Right. So first thing you should notice here is that because the right-hand side, the right-hand side of this equation has I minus 1 and I plus 1, we can only apply that equation to the interior nodes. Okay, so let's do that first. And so let's go ahead and apply it to nodes 2, 3, and 4. Okay, and so if we apply it at I is equal to 2, what we get is B2 at n plus 1 is equal to 4.8, B1 at n minus 8.6, B2 at n plus 4.8, B3 at n. Okay. We do the same thing for I is equal to 3. So we have phi3 at n plus 1 is equal to 4.8, phi2 at n minus 8.6, phi3 at n plus 4.8, phi4 at n. We have phi4 at n plus 1 is equal to 4.8, phi3 at n minus 8.6, phi4 at n plus 4.8, phi5 at n. Okay. So not too bad so far, right? So that's kind of what we've usually done. Okay. And so of course for nodes 1 and for node 5, we can't apply this equation here because they don't have neighbors on both sides. And so, but just like we did in the steady case, we're going to use the boundary conditions for nodes 1 and 5. Okay. So let's go back to the original problem statement and see, what the boundary conditions are. Okay. And so on the left-hand side at node 1, we have a Dirichlet boundary condition, right? So phi has to equal 1 on the left-hand side of the domain. Okay. So this is our Dirichlet boundary condition. And on the right, we have a Neumann boundary condition. So let's factor those two boundary conditions and let's form their usual form. And so, let's write out their equations as if it were a steady one, and then we'll make the modifications for unsteadiness. Okay, so node 1, at node 1, we have a Dirichlet boundary condition. And so we have phi1 is equal to 1 in this case. Okay. So that's how we normally would do it in the steady case. Okay. But of course, now we're in the unsteady case. And so we have to modify this to work with our framework above. Okay. And so to get this to work in our framework above, we have to modify this so we get an n plus 1. Okay. And so we need a phi1 n plus 1 in this equation. For it to work. Okay. Luckily for a Dirichlet boundary condition, this is actually pretty straightforward, right? So we have phi1 is equal to 1, okay? And there's no restrictions on the time here. So all the problem told us is that the phi value at the left-hand side has to equal to 1, okay? And so that means that this boundary condition is going to be valid at all times, okay? And so, we could say phi1 at n is equal to 1. That would be correct, okay? Because it should be valid at the current time. But what we can also do is that we can say that phi1 at n plus 1 is equal to 1, right? Because if it's valid at all times, that means it's going to be valid at the next time step as well, okay? So let's use that for our I is equal to 1 equation. And so we use that, we get phi1 n plus 1 is equal to 1, okay? All right, question, can I repeat the valid at all times again? Yes. And so this Dirichlet boundary condition that we have, if we go back to the original problem statement, stated that phi at x is equal to 0, comma t is equal to 1, okay? And so that means that at all times t, then this Dirichlet boundary condition is going to be valid, right? So no matter what, so until the end of time, the phi value at that left-hand side is going to be equal to 1, okay? And so because it's valid at all times, we can kind of arbitrarily assign any kind of time step value to them. And so, I just put an n plus 1 there because it's going to be valid at the next time step. Okay. Okay. And so at node 5, we have a Neumann boundary condition. And so let's write out the usual form. So our boundary condition here is d phi dx is equal to 2. Okay. And so if we replace this with the finite difference, we get phi 5 minus phi 4 divided by delta x is equal to 2. Okay. So that's what we normally would have. But just like we did with the Dirichlet boundary condition, we need to modify this. Okay. And the way we need to modify is that we need to get a phi 5 n plus 1 somewhere in the equation, okay? Because that's what's going to let us fit it into our framework. And so very similar to the Dirichlet boundary condition, this is going to be valid at all times, right? And so, this equation here is going to be, valid at time is equal to 0 and time is equal to infinity, okay? And so because of that, we kind of have some freedom here. So let me start out by applying n plus 1 to phi 5, okay? Because that's exactly what we need from this equation. So I think, that part kind of makes sense. Okay, so then the question is, what do we do with phi 4 here, right? So we already have our phi 5 n plus 1, right? We actually only need 1, and actually we only want 1 n plus 1 term when we're doing explicit Euler. Okay. Because if you have multiple n plus 1 terms, it actually makes it a lot more difficult to solve. And that actually gets us into our second method, which we'll cover next week, which is implicit Euler. Okay. The good news is that because this boundary condition is valid at all times, we have a bit of freedom in terms of how we select the time index. Okay. And so it's going to look a little bit wonky, but basically what I'm going to do is for the phi 4 value, which is the non-interesting value here, okay, I'm going to assign a time index of n. Okay. So now that we've assigned these time indices, let's solve the equation for phi 5 n plus 1. Okay. So we have phi 5 n plus 1 is equal to 2 delta x plus phi 4 at n. Okay. And so let's fit that back into our system up here. And so our final equation, phi n plus 1 is equal to 2 delta x plus phi4 at n. Okay. Oops, I should have made it a different color. And so that right there is our set of algebraic equations to execute this time marching scheme. All right, any questions on this? All right. And so, now that we have these equations, the next step is to actually, start to use them. Okay. So now let's talk about how we actually use these equations to march forward in time. Okay. First thing we're going to do, our favorite thing to do in this class, absolutely favorite thing, is to take those equations and put them in matrix form. Okay. All right, so the matrix form of these equations would look like this. So we have phi1, phi2, phi3, phi4, phi5, okay, at n plus 1. Okay, so that's all the left-hand sides of the equations. Okay. This is going to equal to a large matrix the first row in the matrix is going to be all zeros. And this is going to be multiplied by phi1, phi2, phi3, phi4, phi5. Okay. All of these at time step n. Plus, we have kind of an extra vector here. Usually this extra vector has to do with the boundary conditions and the source terms. Okay. And so for this particular problem, we have 1, 0, 0, 0, and 2 delta x, which I guess we can plug in for that now, because delta x we know is 0.25. And so 2 times delta x is going to be 0.5. Okay, so let me go ahead and fill in all the rest of the coefficients in that matrix. And so we have 4.8 minus 8.6, 4.8, 0, 0. Okay, we have 0, 4.8 minus 8.6, 4.8, and 0. And we have 0, 0, 4.8 minus 8.6, 4.8. Okay. And then 0, 0, 0, 1, 0. Okay. So all I did there was I just, just like we usually do, we had a set of equations on one side and they all involve phi. And so all I did was I just extracted those coefficients into a large matrix. Okay. So now that we have this matrix form of the equations, we can actually start advancing this forward in time. Okay? And so the way we do that is we plug in, I should say, start the time marching by plugging in we're going to plug in the initial conditions for phi I at n on the right-hand side. And so what that means is that on this side of the equation here, okay, you can see here that we have this phi1, phi2, phi3, phi4, phi5 at n, okay? Remember, that represents the solution at the current time step. Okay? And so the current time step is the first one. And so at the first time step, the solution takes the form of the initial conditions, okay? And so just to remind you, our initial condition is the phi of x and t is equal to 0. Okay. Our initial condition is that we start with the value of 0 at all values of phi at the initial time. Okay. And so the way that we incorporate that is that we have this vector here. Bless you. And then for all the values of phi in this vector, we're going to plug in 0. Okay. And so for phi1 at n, I'm going to plug in 0. Okay. phi2 at n, 0. phi3 at n, 0. phi4 and phi5. Okay. So that's what we're going to do initially, right? So we start with our initial condition, we plug it into the known solution at n, and then all we do from here is just perform the matrix vector multiplication. So we multiply this matrix, here we go, by this vector, okay? And we add this vector, okay? All right, and so if we do that, okay? And so if we perform those mathematical steps, okay, so the matrix vector multiplication and the addition of the one on the right, okay, the first step is usually pretty simple because we start out with a solution of all zeros, it's going to completely wipe out the matrix, okay? And so all we're left with is just the right-hand side. So what we get from that is the following. So phi1, phi2, phi3, phi4, phi5, okay, at n plus 1 is equal to 1, 0, 0, 0, 0.5. And so what we have here, this vector 1, 0, 0, 0, 0.5, this is the solution after one time step. Remember, our time step size is 0.1 seconds. And so after 0.1 seconds have passed, that's what our solution looks like. All right, so now here's the key to the whole operation, right? And so of course, we're not just interested in the solution after 0.1 seconds. We want to find out what's going to happen after 0.2 seconds, after 0.3, 0.4, 0.5, right? And so we want to see, or we want to observe how this solution is going to evolve as time progresses. Okay? So this solution and so this is not the only change that's going to happen. So it's going to keep changing. Okay? And of course, we can use the exact same tools that we have already to solve it. Okay? And the key now is that now that we have solved this, So now that we've solved the solution at the first time step, now all of a sudden this solution here becomes known, okay? And so now we're gonna use this equation or use this vector, plug it in for phi n, okay? And then solve for the next phi n plus 1. So let's see how that looks like. So if we go back to our original matrix equation, so we have phi1, phi2, phi3, phi4, phi5. Okay. All at n plus 1 is equal to our matrix, which is 0, 0, 0, 0, 0. 4.8 minus 8.6, 4.8. 0, 0, 0, 4.8 minus 8.6, 4.8, and 0. Okay. 0, 0, 4.8 minus 8.6, 4.8, 0, 0, 0, 1, 0. Okay. So if we go back to the original form of the equation, this would be phi1, phi2, phi3, phi4, phi5 at n plus 1, 0, 0, 0, 0.5. So this is just just a copy of our original equation from above. Okay. Right. But the reason I copied it again is just to kind of illustrate to you how we can use this for all the future time steps. Okay. Because what we did, basically 5 minutes ago, what we did was for this vector right here, we plugged in our initial conditions. Okay. So that's what we did with this vector. Okay. But we've already solved for the solution at one time step, so we don't need the initial conditions anymore. Okay. And so now let's plug in our solution from the last time step. And so instead of these, okay, if you remember from our last time step, we would get 1, 0, 0, 0, 0.5. And so just like we did before, we're going to perform the matrix vector multiplication and then add that additional vector to the end. Okay. This was going to be a little bit more interesting because we don't have all zeros. Okay. And so the result of this is we get the 1, 2, 3, 4, 5, n plus 1 is equal to 1, 4.8, 0, 2.4, and 0.5. Okay. Right. And so that right there is a solution after 2 time steps. Okay. And so if you want to see the solution after 3 time steps, you just repeat the process. And so you multiply by the same matrix. So the good thing is that the matrix doesn't change. The only thing that changes here is your vector of current solutions. Okay. And so for the next time step, you would take this, you would plug it in there, perform the matrix vector multiplication, okay, get a new solution vector, then go back and plug it in, and so on and so forth. Okay.
Is that the Fourier way?
Is that the what?
Is that the Fourier way?
Exactly. You're exactly right. So, what we'll cover next week, the first thing we'll cover next Monday is we'll see how this looks like in a loop. Okay. Because just like, just like as you can see, this is a very loopable algorithm. Okay, so basically repeating the same algorithm, the same computation over and over and over. Okay, and eventually, you loop this enough, and you save all the solutions, and you're able to get an animation for the result. Okay. All right. Any questions on this before we wrap it up for today? A question on the homework. So why did I use forward and backward for 2b again? It depends on the direction of the velocity. So if the velocities are positive, then you use backward difference. If the velocity is negative, then you use forward difference. Yeah. Yeah, and you have to look at the sign of the velocity kind of in the original equation. And so if you kind of already manipulated the equation a little bit, the sign kind of gets lost. And so you need to look at the original equation and look at the sign to determine if it's forward or backward. Yeah. Okay. All right. So if that's it, that's all I got for today. And so I'll see you guys all on Wednesday for the midterm exam. And so remember, cheat sheet, writing utensil, calculator, and sleep. I guess you'll get some sleep before the exam. All right. So I'll have one more office hours on Wednesday before the exam. So feel free to stop by. I'm going to post the solutions for homework 3 tonight, and so you'll have that for you to study. But if not, best of luck, everyone, and I will see you all on Wednesday. Yes, I should be. Yeah. So I'll be available at 8:15.